dear colleagues, this is our today's colloquium talk. Let me introduce Dr. Emilya Yordanova. She is from the Swedish Institute of Space Physics. She started her career in Bulgaria at the Space Research Institute of Bulgarian Academy of Sciences in 2002. Between 2003 and 2005, she was a visiting researcher at Space Research Center, Warsaw, Poland, where she also finished her thesis work. Later, from 2005, she moved to Uppsala as a postdoctoral fellow. And in 2008, she was a postdoctoral fellow at International Space Science Institute in Bern, Switzerland. Afterwards, she moved back to Uppsala. From 2016, she is a research scientist until today. She was involved in different projects. Swedish project, the last one from 2016 to 2021, was the Swedish Contingency Agency project. This is a governmental organization, and this project involved more than 2 million euros. There were several Swedish institutions involved. Then she was a co-PI of European FP7 project on turbulence in the solar wind and in planetary environments. She supervised also 5 bachelor students, 4 master students, 1 PhD students, supervised and co-supervised 5 postdocs, and so on. She is also a board member of Swedish Physics Society for Equality, Diversity and Inclusivity, and a member of the committee in astrophysics and astrobiology, Nordita, Sweden. I think it is a long enough introduction. Emilya, the stage is yours.
Yes. First of all, thank you very much for inviting me to come here. I haven't been, I think the last time I was here was more than 10 years ago. And I remember I had very nice memories of this visit. So, but it was nice to see that nothing has changed, apart that I see many new faces. So it means that there is a heritage, but also some progress. So that's nice. I was thinking what I'm going to talk, because I was trying to go back in years and remember what I've been doing. Okay, something happened. Somehow. Lost the hearing. Yes.
Good. Yeah.
Yeah. So then I was thinking that the thing that is uniting my research is that I'm doing space physics. So I have covered places in the entire solar system. So it is like local plasma universe that I've been looking at. And it was done mostly from spacecraft measurements. This is what I do. So, and then I was thinking, okay, plasma universe. Then I came across this website called Plasma Universe, where I saw this quotation: no plasma, no 99% of the universe. And then it's really like if you have no plasma, then it means you have no universe. And then it turned out that actually this kind of current plasma universe was coined by Hans Alfvén, or how the Swedish call him Alfvén. So it's a real thing. yeah, this is, I was not expecting that Zoltan will say some words about me, but he heard about my background, so I was moving around in Europe. Things that I'm going to cover in this talk are, of course, starting with the sun, the solar wind, whatever comes out from the sun, the solar storms, and they are called also transients, everything that is in the heliosphere, and then how these things couple, especially to when they come to Earth with the plasma environment of Earth, and especially the side or the interface region region between the solar wind flow and the Earth's magnetosphere, which is the magnetosheath. So it's kind of, it goes from macro to micro physical processes. And there is one common denominator in all of this picture is that all these plasma environments, they are turbulent. And turbulence is filling the heliosphere. And as I said, I've been studying all these phenomena using spacecraft measurement in situ. So these are some of the missions that I worked with. So it's not in any way exclusive, because it just I've worked with these missions. So yeah, this is the main celestial, the major celestial, more important body that controls everything in the heliosphere. Well, that's actually the reason that we have a heliosphere is the sun. So everything starts with the gas that is emanated also from the solar corona, and we have magnetized plasma, which is very important as well. So there are two major components of this these are the slow wind, which originates from the regions, these called helmet streamers above the closed field lines of the solar magnetic field. And then we have the other one, which is the fast solar wind escaping from these open field lines and from the coronal holes, which are, if we could thinking about nice dipolar magnetic field of the sun and the solar minimum, which is almost never the case, but they escape from these polar regions. And then, as I said, when they move away from the sun, the speeds, so radiation escapes, the particle escapes, and due to the sun rotation, we have this kind of a spiral formed. So eventually the fast wind will catch up with the slow wind, and we have this so-called interaction regions where the fast wind is slowed down, the slow wind is speeded up. So it's a complex region and a lot of physics is happening there. And often when we measure, when we observe the same after one rotation of the sun, we happen to encounter the same structure, then this interaction region is called co-rotating, not stream interaction anymore, but it's co-rotating because it means that it had made at least one rotation. But these usually are developed further away than 1 AU, Mars and so we usually, well, with new spacecraft like Solar Orbiter or Solar Probe, we talk about stream interaction regions. And then another large-scale structure that we have is the heliospheric cone sheet. So this is this kind of ballerina skirt structure, which is caused because, first of all, the sun rotates. We have differential rotation. Also, the equator rotates faster than the higher latitudes. Also, we have a few degrees difference between the dipolar axis of the sun, the magnetic field, and the rotational axis. So this is why it's kind of tilted, and therefore you get this kind of beautiful ballerina skirt surface. And this is the surface, this is the hemispheric current sheet, the surface which separates the two polarities of the solar magnetic field. So the solar magnetic field points in this direction here, and on the south, in this case, in this direction. So here, where we have antiparallel magnetic fields, we have this surface, which is very country. And this also is, you can, I don't know if you can see, but here are the planets embedded in the, so it's enormous structure. Again, we will embed this here. And Sun is an active star, so we have a solar activity cycle, which everyone knows. It's measured by the gradual appearance and disappearance of sunspots. So this is a very nice composite image from the Solar and Hemispheric Observatory, SOHO. So we SOHO was operating from 1996, and you can see how you gradually get, it's darker, the sun is darker or brighter. So all this you can follow. You start from something like a ascension phase of the solar cycle. You have a maximum here, and then you go to minimum, and then you go to maximum again. So this is the 11-year cycle. And here it ends at 2020, the last image, but now we are 24. And if you follow the news, you know that recently there was a huge amount of activity, aurora, especially very much south, even probably here, if it was not raining, probably some. So now this, I don't have the updated version, but we will probably have some stuff like this instead. Yes, so occasionally from this kind of, from the sunspots, or which are part of the active region, so-called, of the sun. So at least you have this kind of eruptive events. So depending on the nature of these eruptive events, you can get different effects when it comes to how they affect, for example, the Earth environment or Earth's magnetosphere. So you probably have heard here about space weather, but in very loose terms, I can, the definition for space weather would be that whatever solar activity happens, and it has some sort of effect, usually apart from the aurora, which is beautiful, then everything else is harmful for human technology in space, or also human activity in space, and human technology on the ground. And this is kind of the loose definition of space weather. If you look at the COSPER roadmap for space weather, it's half a page, the definition of what exactly is space weather, but it's not so important. So here briefly, the major, what is considered as solar storm. So if you hear or read somewhere about solar storms, so they can be solar flares, which is simply sudden lighting in brightening, like in this spot here, which because it's light, it travels, it takes 8 minutes to get to Earth, and it affects usually the day side of the magnetosphere or the ionosphere, because it ionizes the UV light, ionizes the particles that are in the ionosphere, and you get, because of that, you get this high frequency communication disturbances or radio blackouts or navigation errors and things like this. So this is usually happen when you have a solar flare and you have an effect almost immediately in the Earth environment. When it comes to coronal mass ejection, so this is massive explosions of matter in the magnetic field. So because then it's charged particles, it takes, because it's plasma moving now, it takes several days. So let's say depending on the speed of this cloud of charged particles, then it can take from 2 to 4 days, something like this. Maybe even less than 2 days if there are really these extreme, very fast events. We are talking about 2,000 kilometers per second or something like this of the CME. And then these are actually the ones that cause serious ground disturbances globally. So you can have loss of power, electric power, because they induce this so-called geometrically induced currents. I will come later to that. But if you know, there is one very famous solar storm, which is called Parenting, by the guy who actually made the connection when we saw the flare, and then later there was this was in the 1959 or something like this. But it was before we got this advanced technology, so there was only telegraphs and stuff like this. So it was a massive event. You got aurora over Hawaii and Mexico and places like this, really, really south. And there were some telegraph telegraph was disrupted by the electricity that was running through the wires, things like this. Had this happened today, it would have been a really serious damage of some estimations amount to trillions of dollars only in Northern America, only from the loss of electric power. So when you think that we are totally dependent on electricity, then it just I can't comprehend the damage that it might happen. Yes, and then we have sometimes from the same region, you can have simultaneously a solar flare that is accompanied by a coronal mass ejection. And then these events are called solar particle events because the effect is accelerate from the CME shock. You accelerate protons and electrons to really, really high energies. So these are radiation storms basically. So if you have something like this and you have astronauts fixing something outside the space station, they should immediately go and hide somewhere where you can reduce the effect of the radiation. And then all this, of course, radiation will damage satellite electronics, so you get all these false signals, and it really disturbs the electronics, and you again you get navigation positioning errors, and it's also dangerous for high over the polar cap, especially. South Atlantic, over the polar caps, high altitude planes, because you really fly high up, and then the magnetic field lines converge at the polar cap. So all these particles, they follow the magnetic field, so they sort of in the hemisphere and the atmosphere. So this is why if you fly there, it's especially for not so much for the passengers, but for the crews of the airplanes, because they are doing this more often than maybe the passengers. Yeah, so these are the major eruptive events that are relevant for space weather and which are known as solar storms. Yes, and so keeping in mind all this complexity, now we have the two components of the solar wind, we have all these eruptive events and everything is going away from the sun, expands, mixes. So you can imagine that this unstable and evolving all the time. So one can really say that the heliosphere is the turbulence in the heliosphere is really everywhere. So I just listed from what we know, what we have measured. We have the solar wind is turbulent, the planetary magnetosphere, stellar winds, we know this, we haven't measured, but we see. Yes, supernova readiness, fusion devices work. So I thought that the putting ingredients from the heliosphere and asked AI to create me an image of turbulence in the heliosphere. So this is what I wrote. And I think it's kind of nice. I like it. You see these different things in the sun is in the center, and it looks at least very much like some turbulent water or fluid flow. Yeah. Yes. So I'm talking about this space weather effects. So the major one from CME, or one of the major ones, is the. And as Lotan said, I led a big project in Sweden where the objective was that we try to understand when the CME arrives, how it disturbs the magnetosphere and the ionosphere and the ground, particularly when it comes to the location of Sweden, because Sweden is located in high latitudes, and these are the latitudes that are mostly affected from this kind of disturbances because of how the solar wind couples with the magnetosphere. I mean, this is a huge field. The only thing one should remember that you need to have this kind of very strong driver like the CME that can cause serious problems on the ground for this geometrically induced currents, and then you need to have a long conducting line, something like power lines, gas pipelines, or railways. So some big metallic structure, because then you get the ionospheric disturbance produces a surface electric field, which drives this kind of strong DC currents, but you need to have a long conducting wire for structure to drive this current. Yes. So we were particularly interested in one set of coronal mass ejections, which are called halos, because of the way they appear in coronagraph images. So here, this is from the SOHO spacecraft. There are two coronagraphs which have different field of views, like several, up to 6 solar radii, up to 30 solar radii. And when a CME like this is directed towards the Earth, these are very wide, very energetic coronal mass ejections. They look like a halo when you coat the solar disk. And with models, you approximate this as a flux rope, which is this. It's not very well seen, but this mesh, and then shockwave as this ellipsoid. And so these are why they are interested, because since they are Earth directed and they are very energetic, they are the ones that cause the most intense geomagnetic storms. But because they are Earth directed, and we see everything, see the light, the features of the CME projected on the plane of sky. So it's very difficult to estimate accurately the speed with which this structure is coming towards us. Even often you don't know until some time whether this structure propagates towards Earth or it's originated from the backside of the sun and it's going away. So they are very difficult to sort of to predict their arrival, because we have these kind of projection effects that lead to a lot of inaccuracy in the CME forecast. So we have difficulty to estimate their kinematics. So we chose a small set of CMEs, halo CMEs, with similar characteristics, because we want to understand how to improve, what to put in the models to improve the forecast of such events. So these halo CMEs, they are very fast, so above 1,000 kilometers, it's a one CME, very wide, very directed, and we know that these particular ones, they had a G effect, so they caused disturbances on the in various ways. And okay, this is a sketch what a CME looks like. So you have this kind of eruption. It's a huge magnetic flux rope expanding away from the sun, which is pushing everything that is ahead. So when it's faster than the background, you create this kind of shockwave. And if you measure this with a spacecraft somewhere sitting, let's say at 1AU that we usually, before some recent missions, we were observing, then you will measure, you're able to identify these regions in the data. So this is magnetic field, velocity, temperature. Then you see this is kind of something, an undeserved solar wind, and then comes the shock. So it is jump, sharp change in all the parameters. And then you have this kind of very fluctuating, very variable part, which is the so-called sheath, because this is compressed and heated sheath, solar wind. Actually, this is modified solar wind that is allowed by this magnetic structure that is coming behind. And here you can see also the flux of very nicely. So when you compare this variability with this here, you see that it's very like coherent, smooth, non-varying structure, which slowly rotates components of rotating, which is represent this kind of variation of the flux rope. So you also see this kind of counter streaming electrons, not here because I don't have this particular one. But it's a very distinct feature when you measure in spacecraft observations. And what we are interested is in this time when the CME shock arrives, because this will act like a hammer to the magnetic field, because with that dynamic pressure, you have a jump in the density and the velocity, so the dynamic pressure is very high, and then you have later with the orientation of the magnetic field is very important, together with the velocity. Then you create this. This is the electric field of that drives the convection in the magnetosphere, and it decides also the orientation of the magnetic field decides whether it will the CME will couple efficiently with the magnetosphere or not. So we are really afraid if the BZ component, this is if the magnetic field is oriented southward, because this means that it will be oriented anti-parallel to the geomagnetic field, And this means that when they are opposited directly, they will reconnect. I will also come later to the reconnection part. Yes, so, okay, then we used few models to compare the models and also to see what is missing in the models and how we can improve the forecast with this particular CMEs. So here I'm just quickly showing the recipe that is usually used in the numerical modeling, from which you can get actually time variation, time profile of the density and the velocity of the entire, let's say, heliosphere up to whatever we want. We usually are interested in what it comes to one view. So these models cover the time profile from up to 2 AU or 10 AU, depending if we're interested in also to see the impact on Mars, for example. So the most common models are this Enlil and Euphoria. One is American, one is European. Generally, we have the long stuff. So, but the principle is more or less the same. You have this the photospheric magnetic field. So you use this as an inner boundary of this this recipe, and there it gives you the model. You have another model which is called Monchili, where you use the bottom of this the synoptic magnetograms, so to get the solar surface from which the magnetic field is assumed that it propagates radially. It's just radially oriented. And then you insert in this environment, you insert the magnetic coronal ejection in a certain form. Usually, what is mostly used is you approximate the CME as a cone. So it's not just a plasma globe, but it has a certain geometric form, which you defined by inserting the speed, the initial speed of the CME and the width of this cone, and you put where actually the origin of the solar source coordinates. And then you let this thing propagate in the environment that you have simulated before. And then you get as an outcome, you have the profile of the density and the velocity. So you propagate the structure, assuming that everything in the background is kind of homogeneous and not changing. So this is very important because we know that in reality this is not the case. All the time you have everything in motion. So here, these are the results. So I will try to walk you through this figure quickly. So in this, the trial itself are different models. So as I said, we've been testing Enlil and Euphoria, which are empirical, numerical, and then we have also empirical models. This DBM, which is drag-based, and EM is you assume some effective acceleration, so the CMEs are accelerated or decelerated by the background. So the empirical models, they don't produce time profiles, so you have they give you just the time of the arrival of this structure. So they are shown with this vertical line. So here is when the CME arrives from the in-situ observation, which is this gray lines. These two panels are the radial speed and the density from Enlil model, the time profile of Enlil. These two are the radial velocity and the density from the time profile of Euphoria. Again, with the observations the actual observations, and then we have the DGM and EM vertical lines. The different shades here, so you should think, think that so these lines are, the models are the prediction, okay. So we have the observation, and this is what is our forecast, space weather forecast or CME arrival forecast. So we have a group of curves here, group of lines here, and we see what we think we are far away from this actual arrival. So our forecast is very inaccurate. So we are underestimating the arrival time. So we predicted that something will come one day earlier than it actually came. And this is not good if we want to do some mitigation, which is a very long story. But let's say you don't want to call a power company and say, cut out your line going that way one day, and they cut out the power and people are without electricity, and then it turns out that nothing has happened. Not good. So what we did, we tried different things. So we refined the input. So here we run models without doing any picking of the fine tuning of the input. But then we invented some clever ways, and we refined the input, which in very roughly we considered what is actually the actual background, what is the actual solar wind. So we include sort of the effect of the solar wind in which this CMEs propagate. And if you just notice that the group of the inaccurate prediction got shifted much closer to the actual observation. So we improved the forecast. Which is like the major result is that we really need to consider what kind of background we put in the models, so we actually get an accurate prediction. And this is not done in the nowadays routine forecast, because there are places like Met Office or NOAA, which are doing this everyday forecast for space weather. They are, because you have to remember that these are different domains coupled, and each of them has its own physics, its own models, so they are not really coupled in most efficient way, or it's not possible actually, because we are bounded by computational power. But we have to keep this in mind, that we need to, it really needs to become integral part from the operations. Yes, so now I am moving more toward the, because you see the effect of the background, people are trying to model actually the solar wind, but we still don't understand much about it, because simply we haven't sampled it away from 1AU. At 1AU we have the solar monitors that measure plasma, but before, back in the 80s, late 80s, we had Helios spacecraft, which went close to the sun, up to 0.3 AU. Now, since I don't remember when solar Parker probe was launched, but some years ago, this was the second spacecraft that actually went even closer to the sun, and solar orbiter is now. But before that, it was Helios and Ulysses. Ulysses in the 90s. It went from 1.3 AU all the way to the orbit of Jupiter. And the unique thing, which is still unique until today about this mission, was that it actually had this kind of polar path, because it went over the polar regions of the sun, so it can see, not really see, because it didn't have an optical instrument, but it can sample the solar wind that is coming from the polar region of the sun. And also to measure really in nice resolution the solar wind all the way to the Jupiter orbit. So I've been working with this spacecraft, and here this is just showing how is the orbit as a function of the years, and here also as a function of the latitude. Because usually all spacecraft that we use, they are in the ecliptic, so they are around 0 degree, plus minus something degrees. But Helios went all the way to 80. So this is, and then these vertical lines are the data intervals that I. Yes. So important thing about I was speaking about the two major components of the solar wind, which is fast and slow wind, which usually are separated just simply looking at their velocity. So if you have higher than 450 kilometers per second, we talk about fast wind, and if it's below, or depending, I mean, it's a matter of taste, but let's say somewhere there. Actually, again, keeping in mind that the things are expanding and they're mixing in the heliosphere, this is not the most precise way of separating the streams. The more precise or accurate way is to actually be able to say where they come from, which is the source region of these streams, to be sure that, okay, now we are talking about really fast stream coming from coronal holes, or the slow wind from the somewhere the streamer belt. So in addition to what you usually know about the characteristics of the fast and slow wind, so this is magnetic field measurement in some days on the x-axis, and this is the radial speed. So you see these variations of it: faster, higher speed, lower speed, higher speed, which coincide with higher. So slow wind usually is strong. You have a strong magnetic field, and vice versa for the fast. But if you look at the charge state composition, this is where you actually see you can add to the magnetic field and the velocity, because this thing stays sort of unchanged when the solar wind expands. And also the plasma temperature or the coronal temperature. So then you have a more, because of course the solar sources have different properties themselves. So then when you combine everything, then you separate the streams more accurately. And then we can look at the turbulence properties, and then you can sort of be more comfortable in interpreting your results in the different categories of streams. One of the most how to say important properties of turbulence is so-called intermittency. And I'm trying to explain how we could see different spectral observations. So this is magnetic field measurement from Ulysses again. So we have on top about 1 month measurement of the magnetic field. And if you zoom in and take 1 day window, and you look at the fluctuations of the magnetic field, you see this kind of video. You zoom in and hours. It's kind of okay. It reminds you see the same features, but you can look at it in a different way. So here this looks very kind of similar, but when you start to zoom in, you start to see quiet regions and this kind of dance more visible. So you increase you zoom in the scale. So actually you decrease the time scale, and you start to see this kind of bursty events, which if you do some statistics on that, this will become much more important in comparison to if you do something like this here. So, and this is kind of, you can consider this as an explanation for intermittency. We can put a measure to it, which is called, people use it often, is flatness, because it is exactly a measure. You quantify this kind of spikiness or quietness of event. And you find this way it's normalized high order or fourth order structure function, which is this increment. So you have the signal, let's say it's this magnetic field, then you take some sort of a lag and you calculate the difference over a certain time scale. And so what you expect is if you focus on increment, calculated for the 3 components of the magnetic field as a function of the time lag or time increment that goes into this structure function. And what is expected is that this flatness scale should increase when you go to smaller scales, as I showed you on the previous, because going towards the smaller scales, these things should become very important. The bursty or the energetic part of the signal should be more important. And this is what you see. So here we have, this is a time scale in hours, and this is seconds. So all this measure, the intermittency increases when you go to the smaller scales. So here I'm comparing the fast and the slow wind. What you immediately see if you compare these two plots is that there is no difference between the components, so the vector is quite homogeneous, which you also this is the fluctuations of the components. If you plot them versus each other, you get this kind of sphere. So it's the magnetic field is one in the direction. So fast wind is really homogeneous. Or much more homogeneous than eccentric. And when you compare it to slow wind, we see the same thing. So you go towards the to the small scales, and the intermittency increases much more. It's much stronger than in here first, and then the 3 components behave differently. So you have some voice here, so where you have no fluctuations. In these directions, you have no fluctuations. So also one thing that you can think about is that when you approach this line here, so all the fluctuations are uncorrelated. If you compare where this happens, it's different time scale for the slow and the fast wind. So the fluctuations start to uncorrelate for the slow wind much later in time, let's say days, than compared to 1 or 2 days for the fast wind. So you're really dealing with plasma that behave differently. And you have different materials. So the slow wind is more intermittent and much more structured than the fast wind. And there is also the variation in how they behave in the solar minimum and solar maximum. Another thing which we were able to assess was this didn't have enough resolution to go to small to reach the electron scales or ion scales. But with our spacecraft, we looked at the fast wind further down. So we went really somewhere there in this plot, and we saw also that the fast wind becomes more scale variant. So it really didn't matter much to be the same temperature as probably. We haven't done this for the slow wind because we didn't have data to compare. Yes, so this kind of complicated, complex solar wind comes to Earth, and the magnetic field of the Earth is very strong, so it's really an obstacle for the magnetized solar wind flow. So because of this, you get this kind of you get a shock wave first of all, which is the Earth's bow shock, and then you get so the color code here is the intensity of the magnetic field. Here is inside this Earth, and you have this. So as I said, you get an obstacle, and you create this kind of sheath, where the solar wind is slow, compressed, seriously compressed here, starting into the wave around the magnetic field. So you create this magnetosheath region. And because you have also, due to the dipole shape of the Earth's magnetic field, there are these so-called casts of the converging magnetic field lines. Plasma from the solar wind or the magnetosheath penetrates way down to the ionosphere. So you can actually heat the ionosphere from you couple the solar wind all the way to the ionosphere with the energetic flux that comes from the solar wind. And one important thing also is that depending on how or where you were in the magnetosheath, actually, you have different geometry, which is defined by the angle between the normal of this shock and the magnetic field, the direction of the magnetic field of the planet here. So you can see from this simulation, this is a simulation, you can see very different behavior of this part than this part. This is so-called perpendicular bow-shock geometry. So the downstream, which is the magnetosheath, has this kind of behavior. While when this angle is smaller than 45 degrees, it's called the quasi-parallel magnetosheath. And you can see here from these are the field lines of the solar wind, how this part is magnetically connected to the upstream. While here, this is not the case. So you can expect that the processes in this part and this part can be quite different. And there's a lot of, like the obvious thing, you see that here the field is much more valuable than here. You have much more structure. You have vortices and current sheets and jets and all sorts of things. Here you get temperature entropy is because of this around magnetic field stronger than in this part. So all this is very interesting, but also very diverse. And we quite a bit about these behaviors from especially two spacecraft missions. This is the cluster mission, 4 identical spacecraft launched in 2000 that were still today operating. Initially, they were supposed to work for 2 years, and we have now 24 years in space. It's really amazing mission. And the spacecraft are located in tetrahedron, like this. So these are different scales. So you can change the configuration. So you can make a smaller or bigger separation between spacecraft depending on what kind of processes you're targeting to understand whether you want something. Oh, really? Okay, I'm halfway through. So you can study different physics. You can, if your separation is something close to the ion scales, then you look at ion physics. If they are smaller, like this was the MMS mission where you could resolve the electrons. You go to even smaller separation. If you want to understand the large scale structure, you separate them and you get the fluid scales. And the importance of these missions also, because of this configuration, you can actually measure, you can separate the spatial variations from the planetary. So for it's amazing that you can measure things in space. The problem is that you measure it in one point, and you are measuring in one point something that you want to infer, then this is the spatial structure that is called in space. So for this you need multiple measurements, and this is what these missions did. So we advanced greatly. And so now I don't know what to do. What thing, where to jump. So let's do like this. So as I said, we have different physics. We're just looking at these plots. You see that the quasi-perpendicular is very different than the quasi-parallel. This is for spacecraft. And it's for MMS spacecraft. What we found that in this part, we have a lot of currents, a lot of structures, which you don't see in the quasi-perpendicular one. So this is very important because these currents are the places where you have many things happen, like magnetic reconnection. You exchange energy, you take energy from the field and you give to the particles. You have a lot of free energy. You generate waves, all sorts of. So this is the microphysics then. So in this work, we confirmed the simulation result, which tells us that in the reconnection process is happening in these places. If this is the distribution of the current from the simulation, the probability distribution, you get the reconnection is happening in these scales in the distribution. And we actually saw this in the observation. This is observation. This is simulation. This is observation. This is cluster. So this was the first observational evidence that we confirmed the simulations. And then another thing that we did was to use a measure or a way to calculate the current when we have single point measurement. Because we show that in this case, when we compare this thing is actually something that you use to measure the current just on single point measurement. And this is the current that was calculated based on the fourth spacecraft. So you see when you do this kind of scatter plot, you see that this proxy is exactly where you have the strong currents. So we can use this proxy from single point measurement to calculate the current when we don't have more than one spacecraft, which is the case in the following. Okay, magnetic reconnection, how you find it. So another important thing is, as I said, in reconnection, so you probably have heard a lot. Here there are people that are doing reconnection all the time. But as I said, you convert energy from the field you give to the particles, and you have also this kind of dissipation measure, electric field and current, they omit heating, which we have observed in the magnetosheath based on the four measurements. So these which spikes here are at electron scales, and you see that you have they are very strong. So this is where we have at reconnection site. So this is the reconnection site. In the magnetosheath, we got this kind of very strong dissipation. Yes, this is further proof from in situ about reconnection, which I cannot talk about. But the important thing is that in turbulent environment, which is a magnetosheath, we can find these features that are expected for the magnetic reconnection, but not exactly nice and clear as if you're observing a reconnection at the magnetopause or one of these large boundaries. And we actually, in this work, we reported the first electron, so-called electron-only reconnection, because you only saw the outflow in the electrons, not in the ions, as you see it in the, which is a feature of magnetic reconnection. So yeah, this was kind of the first magnetic reconnection in the environment.
She's more than 100 times cited today.
Yes. Yeah, I mentioned that you get another way to dissipate energy is through waves. These are my PhD student is working on whistlers in the turbulent magnetosheath, so she did a great job. Now it's they're going to dissipate those out. Just to mention that another way to heat the electrons is to these generations of whistler waves. And of course, turbulence is another way. So you have reconnection, you have waves, and now you have turbulence, another process to heat plasma. And here again, we start from simulations where we show that you have this kind of structures for the system, the currents, the flow vorticity, and the temperature, which look similarly. So these three are heating the plasma. And we looked for this in the data with this, as I said, this proxy, looking at the proxy for the current and the flow vorticity in spacecraft observations. And we use the CME sheath, one special CME sheath region, which is very turbulent. So here is the shock of the CME. So we are in this region. So I'm not going to walk you through all this complicated thought, but the important thing is that when we have collocated current sheets, plasma flows, velocity shears, vorticities, and these kind of structures that are small, that are result of the turbulence, and you look at the correlation regional, like a larger, not point to point, but you take a bigger volume and you look where you have these kind of structures, and you check what is the plasma temperature doing. So you expect that this structure should heat the plasma. If you concentrate on the yellow areas, you see that this is exactly what happens. So this is correlation between the structures of the velocity in the magnetic field close to 1, which are coinciding with these pockets of enhanced temperature, plasma temperature. And you are away from the shock. So here, this is the temperature. We have a huge increase of the temperature just right behind the shock. This is shock physics. It's entirely due to the presence of this shock. But to go further in, so this is like hours later in this sheath region, and this is turbulence. This is the turbulence heating plasma. Yes. Okay, so here I just go to different plasma regions, interaction, different types of solar wind to show, to look for this kind of we expect that depending on the large scale structure, we can have different attitudes. But nevertheless, when we are when we have these kind of groups of or blobs, as we call them, of coherent structures, we can relate to plasma heating, local plasma heating with these structures. So my summary, that in order to comprehend our local plasma universe, we still need a lot of work to do. We need these multi-scale approaches. So we really we need sophisticated instrumentation, but we really need to look at the same time at the different scales and how they are coupled. This is very important. We need also to understand all these structures, coherent structures that I talked about, and because they exist also at different time scales, so spatial scales. What is their nature, and also how they are connected, and how we interplay between them. And of course, we need to understand all these energy conversions and energy dissipation. So we close the terminology.
Okay, Emilya, thank you.